Okay, so this week we are going to do SolidWorks flow sims. Um, Also, I have my roommate Bex is here looking over my shoulder, learning flow sim with me. So um, if she asks any questions, that's who she is. Um, well, yeah, we're doing SolidWorks flow sim this week. So everyone should hopefully have a CAD of their engine, whether it's just kind of a block with the internal nozzle profile in it or something that looks more like this. Either is fine. Either will get you flow sim results. Um, so yeah, let's just go ahead and get started. So FlowSim, everyone should have FlowSim. It comes with the student edition that you all just installed. Um, so in order to get that, so normally it'll open up on the features tab, and you see you have all these different tabs here. Maybe not all exactly the same, but you'll have a bunch of tabs down here. And if you go to SolidWorks add-in, you look for the one that says SolidWorks Flow Simulation and the little picture of the airfoil and the little streamlines going around it. It takes a while for it to load, and now you have a Flow Sim tab here. Hopefully you have a Flow Sim tab there. Sometimes it doesn't load that tab, in which case if you um, I don't know. That happened to me last time where the flow sim tab didn't show up, and I just went to add-ins and unloaded it, and then reloaded it again, and then for some reason it showed up that time. I don't know. SolidWorks is dumb sometimes. You'll just have to work with it. So now we have SolidWorks Flow Sim loaded. Um, we have a bunch of tools up here, but we're not going to touch these yet. So we need to, oh, hold on. I need to delete these so I can show you how to do them later. Um, I'll delete the results later. Um, so you start by going to the wizard. Actually, I guess we'll just start a new project. Um, Startup Wizard, you can just go directly from new project, but then you have to enter all of this stuff manually, and that's a pain in the ass. So just start with the wizard. Um, I'm just going to name this uh, Engine Sim 2. I think I named the old one Engine Sim 1. Um, and then you hit next, and this window is selecting what units you'll be working in. I would suggest staying in SI units, meters, kilograms, seconds, um, since that's for the most part what we've picked for the spreadsheet. If you want to do PSI, you can change that down here. Um, or if you want to, I don't know, do inches or set this to like millimeters, you can. I would just leave it at the default. Um, and then so you hit next. And so now you'll select what type of analysis you're doing. So the first option you have is internal versus external, and this is whether you have internal flow or external flow. Internal flow, like in a pipe or in a rocket engine, it's flowing internally, like the one on the bottom here over in the left pane. Um, and then external is external flow, I guess. I don't know, like if you're simming the aerodynamics of the rocket itself, um, and that's similar in picture to the one on the top in the pane on the left. So we're doing an internal flow. So select that one. We're going to leave exclude cavities without flow checked. That just helps the mesh um, use up less resources. And then here, there's a bunch of other options we can do. So heat conduction in solids is whether you want it to simulate heat transfer through solid surfaces. We are going to leave that unchecked for now, since we're just looking at flow. Radiation is whether you're going to have radiative heat transfer, which we're not going to look at either. So we're going to leave that unchecked. Time dependent is if you have flow conditions changing with time. We also aren't having that. We're looking for the steady state flow conditions, so we're going to leave that one unchecked. Gravity is interesting. We're using such high pressures and velocities and forces that gravity is fairly negligible, so I'm going to leave that unchecked. I also think when Arun modeled this, yeah, he modeled the engine upside down, so gravity wouldn't necessarily be accurate here. So we're going to leave that one unchecked. I honestly don't know what rotation and free surface mean. But I've never checked them, so I'm going to leave them unchecked. If anyone figures out what these mean and thinks that it applies to their simulation, by all means, but I don't know what they are. So now we go to define our fluids. And so we're going to use air as an approximation, ideal air, which starts with A, haha, is at the top. So you're gonna click on air, make sure it's selected as the default fluid. We're using air because, well, all of your combustion gases are probably going to be different, considering you all are using different fuel and oxidizer combinations with different combustion conditions and stuff. And those are all very complicated fluid properties um, that aren't a preset in SolidWorks FlowSim. And air is not quite close enough, but we'll pretend it's close enough. If you get some weird results with air, you can actually go and if you hit new, you can define your own fluids. They've changed this with 2020. I don't know which menu it's under, but oh, it's probably under, yeah, material gases, user defined. Yeah, you can add new there. Um, and define your own fluid properties in your own gas. If anyone gets to that point on Thursday's lecture, just ask me and I can help you with that, but I'm not going to go into it for now. We've just selected air, and that's cool. So the other things you can pick are whether you have laminar and turbulent flow. Um, we are just going to cover our bases and say laminar and turbulent. It's probably just going to be turbulent, but want to account for everything. So high Mach number is an interesting one. So we are going to have high Mach numbers, but I'm going to leave this unchecked because the last time I tried recording this lecture, I checked high Mach number flow. I think this is a new feature in 2020, and it really didn't like that. It just wouldn't run the sim. It kept giving me errors, and I eventually figured out that this box was the reason. I don't know why, but leave it unchecked. We're also not going to check humidity, um, oh, because um, we're uh, we're just using dry air as an approximation. So that's that. Um, So next, wall conditions, you can pick in terms of heat transfer, whether you have an adiabatic wall, so whether there's adiabatic means no heat transfer at all. You can set a heat flux, heat transfer rate, you can set a wall temperature, etc. We're just going to leave an adiabatic wall for now since we're not trying to look at thermal effects yet. And you can also change the surface roughness. Um, Smooth wall is zero micrometer. Surface roughness is basically just a smooth surface, and that's a good enough approximation for us, since we don't actually we haven't picked materials, we haven't figured out manufacturing techniques, so we're just going to leave it at 0. Um, and then we hit next, and so now we have a bunch of different thermodynamic parameters. You don't have to change any of this, and I'm not going to touch any of this. This just kind of sets the default for your boundary conditions. You can, once you define a boundary condition, it'll autofill all of these parameters, and then you can go in and change them manually. This is just if, say you want to, actually, why don't I demonstrate and change this now? So since we have a chamber pressure of 2 million pascals. I'm just going to go ahead and change this right now. So 2000000. And we have a combustion temperature. Oh, cool. I have to go find that in CEA. No, this one. We love fishing through the air on U-Drive. Okay, our combustion temperature is 3,850 Kelvin. So that's what I'm going to put in here. 1,850. It is actually pretty important that you set the temperature to be your combustion temperature, around your combustion temperature at least. Fluid properties change with temperature by a very much non-negligible amount, especially when you're talking about something on the order of 3,000, almost 4,000 Kelvin. So that is going to affect things. But also, like I said, you don't need to change this yet. You can leave it as the defaults and change it later, but I just to illustrate now. So now we finished setting up things, and flow simulation is giving us an error. And that's because we're doing an internal simulation, so it wants a closed volume. And right now the ends of the engine are open. So it's prompting you whether you want to open the lids tool to close those. We are going to do that, but I'm going to hit no just so I can show you guys where that tool is if you accidentally hit no. So the lids tool, if you go all the way to the right under tools, drop down, and it's the first one, create lids. And then you just select a planar face and it'll close that face for you. Hit check. And now it's asking if we want to update the mesh. Hit yes. Update mesh again. Yeah, hit yes. Still have the other open end. I'm going to hit no again. I probably should have just done. Now, so this isn't going to work because this isn't a planar face. This is conical, but I'm just going to, yeah, it won't let me select it. I'm trying to click on it here. It won't let me select it. So lids tool will only work if you have a flat face, but don't fear, you can just go and create a lid manually. So right now, also, if the FlowSim tab over here doesn't open automatically, just navigate all the way to the end and you can get all of this stuff. But I'm going to go back to the features tree and the features tab, and actually the sketch tab. Then we're going to select the front plane and try to get normal to it. Create new sketch in front plane, and then just make the sketch of a disc to cover up this the end of our nozzle, and then the specs.
Was that equal to the higher the low point of the
Yeah,
tilted surface?
it's this one's equal to low point. It doesn't really matter as long as it closes. If you make it equal to the high point, it might give you a rebuild error and say like invalid geometry. At which point just make it so that they overlap more. Because yeah, it might give you like a 0 thickness geometry error. Yeah. So now we have our sketch, and we're going to revolve that about the center line there, and just keep it 360 degrees and hit check. And now we can reset the computational domain. and it doesn't give me an error this time. Everything's closed. So cool. Now we can start defining the boundary conditions. Uh, cool, that's covering up. There we go. So go back over to the FloatSim tab we were talking about before. And now important step here. So you're gonna have to define your boundary conditions on the inside faces of these. So you're gonna wanna do section view so that you can have access to these. You can't do section view once you start setting up the boundary conditions. SolidWorks is stupid. You have to do that before you get into the boundary condition creation menu. So make sure you section view and then right click on boundary conditions, insert boundary condition, and we're going to start with the inlet mass flow. So you have to define, first of all, you have to define 3 different types of boundary conditions, an inlet mass flow, an outlet mass flow, and a pressure. So we're going to define inlet mass flow on the lid, outlet mass flow at the end of the nozzle. And then since we know what our chamber pressure is, we're going to define this face as the pressure, but that comes later. So we're going to start with inlet mass flow, select that face. We're going to look to the spreadsheet and find total mass flow of propellants is 166 kilograms per second. Put that in there. Check the thermodynamic properties. See here, remember we input these values before. They pop up here as default, so we don't have to worry about them now. But always double check to make sure those are accurate. And if you didn't put those in before and left them as default, they'd show up as 101 kPa and 293 Kelvin. And you'd have to change them now. So this looks good. Remember the way we rounded this because the outlet mass flow has to be exactly the same. Otherwise, you're going to get weird pressure buildups. Yes, English. Nice. So we're going to check that and then right click, insert new boundary condition. We're going to define the outlet mass flow at the end of the nozzle. This one we just have to put in mass flow. There's no thermodynamic properties because this is an outlet mass flow rate and it's going to calculate what the thermodynamic properties are at this point based on the nozzle and everything. So go ahead and check that. Right click, insert third boundary condition is going to be a pressure opening. I'm going to be honest, I don't know what the difference between these 3 are. I don't think it makes a difference what they are. I think it makes a slight difference, but I've never noticed it to be significant. But so I'm going to leave it as our 2 million pascals chamber pressure. And since there's no heat transfer here, it's an adiabatic wall, temperature doesn't matter. But I just get in the habit of setting the temperature to what the fluid is going to, the fluid it's facing is going to be, or whatever you expect the temperature of that wall is actually going to be. Because one day you'll be doing a thermal sim and you'll forget to set this value, and your temperature values in the fluid are going to be very off, and you're going to spend like half an hour trying to figure out why and figure out it's just because the wall temperature is the wrong temp. Anyway, that's definitely not a true story. Okay, cool. So we've set our boundary conditions, which is pretty much all we really need to do to set up the sim. There's a whole bunch of other stuff that's more powerful you can do. You can set mesh, but we're going to let it auto mesh. So for those who don't know, the mesh is just kind of, it picks the cells and nodes at where it calculates all of the stuff. And if you have small geometry, it's good to strategically select the nodes to make sure you are actually calculating in the areas you want to, or if you, um, for example, if we wanted to make the mesh more fine around the throat, since that's where we expect the most gradient in, like the most difference in flow, velocity, and pressure and everything. We could, I'm just going to leave it at the default because uh, SolidWorks is okay, and we're approximating this with air. So this is not going to be a super detailed simulation. You can also set goals, which are kind of interesting. We don't need any for what we're doing. We can get everything we need by post-processing plots and stuff. But it's, for example, if you wanted to define a surface like at the throat and just, I don't know, see you get the mass flow rate through that surface, or I don't actually know what else you can get from goals. I think goals will also give you a detailed breakdown of what the values are for each iteration instead of just giving you an average of all the iterations of the sim, which I should probably actually explain. SolidWorks is going to just run this like 100 times and it's going to average it for us. And that's what our data is going to be. So if you set a goal, it will give you the results of each one of those simulations. But we don't need any of that. So we're just going to go ahead and hit run. And we're doing a new calculation and we're going to hit run. And you get this little solver window pop up here, and it's going to calculate. Here you have the iterations. Yeah, see, it's giving us a warning about supersonic flow. Box number exceeds. Yeah, that's expected. Again, I tried doing checking the box for supersonic flow, and it didn't like that at all. It at least finishes running. If you don't select that, it'll just give you an error. So that's done now. We can X out, and now we can post-process the results. So our best friend here is going to be the cut plot, which pretty much just, you slice a plane and look at what's going on there. Let me go back. The other things you can do are surface plots, which is just on a surface. I don't know what isosurfaces are. Don't ask me about them. Flow trajectories can get you the little, I don't even know how to explain it. Either like the little balls that you can animate stuff with that, and then if you have like the spaghetti plots, I'll make one in a minute. You'll see what that is. I don't know what the rest of that is actually, but we're gonna go with a cut plot first, and the default is already in the plane that we did the section view in, so that's cool. We're gonna leave it on contours. We want to look at velocity first, and we want just velocity. Don't pick X, Y, or Z, because that'll show it in only one direction. We want all directions of velocity. And you can pick, I like using streamlines for velocity, but it looks like my graphics card doesn't want to do that. So even if I hit yes, yeah, it doesn't want to do that. So that's fine. I'm not mad. What if I do, oh, it'll do vectors. That's cool. For picking the scale of the plot, I usually just, so like click on this little thing, and then it'll auto scale to the maximum and auto scale to the minimum. And then this here is like the number of contours, and I just like boost this up so it looks smoother. And then hit check, and it will look really weird. So we have 55 meters per second in the chamber, and then it gets real fast up to like, what is this? You can actually find specific values here if you go to probe, and look at that. You can see what the value is. So that's like 3,000 meters per 2,700 meters per second. I don't actually remember what we were expecting at the nozzle. This is some weird stuff. Probably probably related to the errors in the solver, but that's fine. We can ignore down there. 2700. If we look at here, exit velocity, would you look at that? About 2700 meters per second. So again, air is not perfect, but it is pretty close, depending on your propelling combination. And then we can go ahead and hide that and create a new one to look at pressure. Do the same thing, adjust to max min, do this one, slide it up. Here you'll see, yep, there's our chamber pressure, about 2 million pascals. It compresses quite a bit at the nozzle inlet, and then it drops rapidly after the nozzle throat, which is expected. And then we get to our exit pressure. This is what I'll call it like 5,000 to 6,000 pascals. And we, pressure ratio of 25 means chamber over exit. What do I divide this by 25? X.
What's happening?
I'm trying to do math and I'm being dumb. Chamber over exit is 25 equals 25. So yeah, it should be this over 25. Gives us 80,000 pascals. And what do we have here? A lot lower than that, but again, that was where the sim was being weird. And also remember, air is not the same properties as the combustion gases. So this is not quite as expected, but also plausible. So those are the two plots you'll probably look at the most in proving the nozzle. There's a bunch of other plots that you can look at here. You can have relative pressure, acoustic power. You can put density. Mach number is also an interesting one to look at. Let's see what we have here. Yeah, it just looks the same as the velocity plot. So yeah, that's that. And now I don't have any of the contours turned on because my graphics card is shit apparently. So we can't look at where the flow is going and whether it's following the walls or whether it's separating, but that's why we have the flow trajectories, which I mentioned earlier. So I'm going to look at the pipes spaghetti plot, as they call it. So basically, you have to pick a starting face. Actually, I don't know if it has to be the starting face. I think I'll just do it for whatever. And I want to look at velocity with this. So here you can select the pipe width. I'm going to do the same plot, min, max. Transparency. Here's the number of pipes that show up. You can also select lines with arrows, bands, I guess. I've never seen that one. Spheres, arrows, all that. Arrows and spheres, I think you can animate. Pipes are just stationary, but pipes look pretty cool. So if I hit check, it's gonna do the thing. And look at that. So the pipes, wow, that's wacky looking. So they flow through the nozzle and they look like they follow the nozzle relatively well. If you get flow separation and that's bad. it'll look like it'll follow the nozzle for a while and then just kind of suddenly cut inwards. That's not good, not ideal. Um, so yeah.
What should they do about it?
Oh yeah, if that starts happening, just make the nozzle shorter, just like cut it off at where the thing is separating. Um, and I'll also show the spheres. Um, and see if I can figure out how to animate it. They changed things, and I'm sad. Oh, oh. Well, I think dynamic trajectories is probably how you animate it, but it doesn't look like my graphics card is going to let me do that. So, oh wait, maybe it will. No, I don't think it will. Well, these can move, and they'll be proportional to the flow velocity. My graphics card doesn't want to do that for you guys though. So, yeah, that's that. SolidWorks FlowSim can be pretty tricky. I did actually run into a few issues the first time I tried to record this video because they have changed some things with 2020. But please don't hesitate to ask us during Thursday's thing if you get stuck and want us to help debug something. And then if you finish this sim, because you already know how to use SolidWorks FlowSim, another thing you can do is change the boundary conditions over here. Instead of just capping the end of the nozzle, you can put a giant cylinder around it and let it essentially, shoot the nozzle's exhaust into open air-ish, kind of, by doing a giant cylinder. And I can hide this plot and show you what I'm talking about, since that was a pretty bad explanation. So if we edit this, oh, shut up. This will be really annoying. And like every time you change something about the model, it'll come up like that. But so if we just kind of delete this whole thing, and then we do something like this. And make sure you close it in this wall, but don't get it inside the nozzle. That wall was very thick. Yeah, so if you do something like that, this is very poorly drawn. It's not symmetrical. But hopefully you guys get the idea. And then you can put the boundary condition on this wall instead of the end of the nozzle. And then you can see whether you're overexpanding if the exhaust gases go out and then go in. You can see if you're underexpanding if they go out and continue to like bell out, or if you perfectly expanded it and they just kind of go off in a straight line. You'll be able to see that. So yeah, I think that's about it for SolidWorks FlowSim. Yeah, I'm just gonna end this video here, I guess.